guess it didn't really crash after all. All right, well, let's do this natural log one. So this one may not look like it's a telescoping series. You don't really notice it until you do until you expand it a little bit. So we know that the natural log has a property. We have the natural log of a quotient. Natural log of a quotient can turn into a subtraction. So this can turn into natural log of the numerator minus natural log of the denominator. And now we see the classic format of a telescoping series is that you have a minus there. You've got two terms, and then we want to figure out if there's going to be a cancellation with that setup. So let's take a look. So S sub n, some of the first n terms, once again, we're lucky here because these first few start with 1. It gets a little more confusing when we don't start at 1. We'll see a couple of those. So we plug in 1, and we get ln2 minus ln1. So that is when k is equal to 1. And then we plug in k equals 2, and we're going to get ln of 3 minus ln of 2. So that's when k is 2. And we're starting to see that, oh yeah, there's a cancellation pattern here. Let's go to k equals 3. So when k is 3, we'll have ln 4 minus ln 3. And we'll go one more term on the front end. So this is going to be when k is equal to 4. So we'll have ln 5 minus ln 4. So these corresponding k values we'll just put down below just so we can keep track. So those are the k's. Now we need to get to the last two terms like we did over there for S sub n. So we're going to have our dots. And then we have to plug in k equals n minus 1 and k equals n. And that'll give us the last two terms of S sub n. So plugging in the n minus 1 here, we're going to end up with natural log of n minus natural log of n plus 1. So that's the n minus first term.
Wouldn't it be n minus 1?
Maybe. So we're plugging in n minus 1. Yes, that should be an n minus 1 right here. N minus 1. And then here we're going to plug in n, and we'll have natural log of n plus 1 minus natural log of n. So that is our nth term. There we go. So that is S sub n. Now we just have to collapse it and figure out what the closed form or the equation for S sub n is. So we'll start doing our cancellation. So our pattern here is a little different. So we go left to right first. So we have first part canceling with second part of next. First part canceling with second part of next. First part canceling with second part of next. This thing is going to cancel with something that's in the dots. First part with second part of next. Now we work from right to left. And you can make sure of your pattern by looking here and just sort of picking a spot and going to the left and making sure you understand what it is. So if we're going right to left, we look here and we see it's the second part cancels with first part of prior. So that's what we see here. Second part of this cancels with first part of prior. Second part right here is going to cancel with first part of prior, which is going to be somewhere in the dots. So the only terms that aren't going to disappear are S sub n will be negative natural log of 1 plus natural log of n plus 1 plus natural log n plus 1. And of course, natural log of 1 is equal to 0. So S sub n is going to be equal to natural log of n plus 1. To find S, we take the limit of S sub n as n goes to infinity, And what is the limit of that as n goes to infinity? Infinity. So our conclusion is, does this converge or diverge? Yeah, so therefore this series is going to diverge since it doesn't converge. If that limit is not a number, then we say the series diverges, if it's not a number. Okay, let's try another one here. This one is sort of set up classically. It's already got the subtraction. We don't need to do anything here. So S sub n, sum of the first n terms. Once again, it starts at 1. That's ideal. So our first term and our second term literally correspond to 1 and 2. Plug in a 1 and we get square root of 2 minus square root of 1. Plug in a 2 and we get square root of 3 minus square root of 2. Plug in a 3. So these are our k values. Maybe we'll just go to 3 on the front this time. 3 is usually enough. 4 really establishes the pattern. 3 is generally enough, though. So plugging in a 3, we're going to get square root of 4 minus square root of 3. And then some middle terms. And then we need to figure out what's happening down here. So we're going to let k equal n minus 1. Let's not try to do anything fancy today. So k is going to be n minus 1, and then k is going to be n. So plugging in n minus 1, we're going to get square root of n minus square root of n minus 1. And then plugging in n, we'll have the square root of n plus 1 minus the square root of n. Square root of n plus 1 minus the square root of n. All right, so we have that. So the pattern is very similar to the last one. We see that the first part cancels with second part of the next. So first part cancels with second part of the next. This square root of 4 is going to cancel with something inside here. First part will cancel with second part of next. And then we establish the right to left pattern. So if we look here, the pattern is second part cancels with first part of prior. So this second part cancels with first part of prior. This right here is also a second part, and it's going to cancel in here with first part of prior. And so we end up with something similar to the last one, where we have minus square root 1 plus square root n plus 1. Of course, the square root of 1 is 1. So this turns into square root of n plus 1 minus 1. So that is S sub n. So if you were dealing with a finite series and it said, what is S sub 100? All you would have to do is plug in the 100 right here. So this tells us a formula for the sum of the first n terms. So just note that if you were asked for S sub 100, that would be the square root of 101 minus 1. Of course, any finite series converges, right? Finite series is finite. You just add up those terms. And so the S sub n is going to give us, whatever we want. If we want the sum of the first 1,000 terms, the sum of the first 1,000 terms will be the square root of 1,001 minus 1. But we see that the infinite series is going to diverge. Because when we take the limit of S sub n as n goes to infinity, that is going to be infinite. So therefore, we have divergence for the infinite series. So the infinite series will diverge, but any finite series would, be finite. Yeah?
And it would be convergence if there was only a constant, correct?
Yes.
Okay.
This has to be a constant in order to get convergence.
Okay.
Yep. like this one up here. So when we took our limit here,
Mhm.
we ended up with s equals 1/2, so that's a constant, so therefore that one converges. Okay, so there are a couple of slides here that I just want to mention that aren't going to be on the test. They're just sort of interesting. They're sort of optional, but just sort of points of interest. So this first one is about Archimedes' quadrature of the parabola. And this is long before calculus, and the question was, what is the area of a region that has a curved boundary? So up until these times, you could only find area of polygonal type shapes where you had sort of straight edges, or a circle, or an ellipse. Few curved objects. But parabolas, they could not find the area of. And so what he did was super interesting. The creation of all these triangles is what happened. And so what we notice is that in the first step, we have this one triangle, and then we bisect and create this point right here, and then form this triangle. Same thing over here. We're going to bisect this interval, come up here, create that point, create those two triangles. And then we're going to keep on doing that. So a sub 3 is going to be the area of the triangle that would fit in here and would fit in here. We're going to bisect both those intervals, and we're going to create a point right there and a point right there, and then form. I'm not going to even try to draw because it gets really messy, but you can imagine two triangles there and two triangles there. Those will be called a sub 3. They'll each have the same area, which is not obvious. There needs to be a little bit of work done in showing that the area of this triangle is going to match the area of that triangle, but it will turn out to be the case. And moreover, the important thing is that a sub 2, the area of this blue triangle is going to be 1/8 the area of the first triangle. And that pattern is going to persist. A sub 3 is going to be 1/8 the area of a sub 2. Totally bizarre that there's this little pattern in there, so that makes it a geometric pattern. Geometric pattern is when you multiply, you have a common multiplier. So you get to the next term by multiplying by some common number. In this case, it's 1/8. So long story short on this, you can add up the areas of all these triangles, and you can then replace each of these triangles with a function of the first triangle, because they're 1/8 the prior triangle. And so when you get it all turned into an equation with just a sub 1, you can factor out the a sub 1. That's a geometric series. When you do the math, there's some canceling up here, and the common multiplier turns into 1/4. So that is what we call the R. So R is 1/4 for that geometric series. And then we use our formula, little a, first term divided by 1 minus the fourth, and we get that the area of the parabola, of that parabolic region, is going to be 4/3 whatever the area of this triangle is initially. And so here's an example. You can look at that carefully if you want. Optional though. But super interesting that geometric series can be used in all these sort of infinite series if there is a pattern that can be found. Finding the pattern is the hard part. So let's talk about some generalities with series. And this should look very similar to the generalities that we see with derivatives, that we see with sequences, that we see with limits. So this first one says that if you have a convergent series and you multiply by a constant, that creates a new series, and the new series converges to the constant times the limit of the original series. In other words, a constant can be factored out of the series. So if you have that series right there where you multiply everything by the constant c, you can factor the c out. Just like you can with a limit. A constant can factor out of a limit, it can factor out of a derivative, it can factor out of an integral, it can factor out of a summation. If you have a divergent series and you multiply by a constant, you can't offset the divergence. If you have a series that diverges, no matter what constant you multiply it by, other than 0, you will still have a divergent series. You can't somehow undo the divergence by multiplying by a constant. You get the classic sum difference one. So if you have two series that converge, if you add or subtract the series, you will still get convergence to a plus b or a minus b, depending on whether you add or subtract. So if you have one series that diverges and one that converges, the sum or difference has to diverge. There's no way you can take a divergent series and add a converging series and offset the divergence. So divergence is very strong. There's no constant you can multiply to undo it. There's no other infinite series you can add to it to undo it. So if the series diverges, adding a convergent series to it's not going to fix it. It's still going to diverge. And then we have this situation that we've talked about before. The first series here starts at 1, and here we have the exact same terms, but we're going to start out later. So we're essentially chopping off the leading terms. Then both those series diverge or both series converge. So if you chop off the first 1,000 terms of a series, it does not affect whether it converges or diverges. Doesn't matter how many terms you chop off the front. Doesn't change diverge or converge. What it could do, if you have a series that converges and you chop off the front, it's going to change what it converges to, because you've taken away some of the terms that are being added together. But it doesn't take away whether it converges or diverges, just what it converges to, if it converges. And so we've talked about this with sequences. Same idea here. The tail of an infinite series is the terms at the end with the large index. Convergence and divergence depends on the tail. That's the important thing for convergence and divergence. The leading terms tell you, more about what it converges to if it converges, but it's the tail that tells you whether it converges or diverges. So here is an example of the Koch snowflake. Koch snowflake is a fractal. And you build this fractal by chopping off middle thirds and adding this equilateral triangular shape repeatedly forever. And this is an example of a curve that has infinite length but finite area, this shape. So the curve around the boundary is going to have infinite perimeter, but the area will be finite. So we're going to find these objects in math as we go on that have these strange properties. So the boundary is infinite, but the inside is finite. And you can do the same thing in 3 dimensions. There is something that will have finite volume but infinite surface area. And it's the same idea. It's got that fractal nature where if you keep zooming in, it keeps repeating itself. And this is an area of math that was not fully developed until recently, in the 70s. So when it really got studied super hard. But it should be pretty intuitive. It's sort of, you've probably heard about the coastline problem. Like if you go to measure the coastline of England and you're using a yardstick, you're going to come up with a certain measurement. If you go measure the coastline of England and use a 1-foot stick, you're going to get a different measurement. It's going to be longer. If you measure the coast of England with a 1-inch measurement tool, accurate to an inch, you're going to get a different measurement. And so these edges can have different dimensions. You can have dimensions that are partial dimensions, which is what the fractal is doing. So instead, like normally we think of a curve as being one-dimensional. But if you start adding all these sort of jigs and jags to it, you can create curves that have higher dimension than 1, but not 2-dimensional. They're not an area. They're not a region. But they have more dimension than 1. So you get these partial dimensions, which creates a whole bunch of interesting problems. So what I did here was set up a table you can look at this if you're curious about fractals. Won't be on the test, but you can look at this and figure, this just sort of goes through the calculation to show that the perimeter is actually infinite. and the area is actually finite. So this table walks you through the steps of how you would analyze something like the Koch snowflake. So interesting example for people that are interested in weird things. All right. So we've now completed the first two types of series, geometric and telescopic. Now we've got to deal with the rest of them. So if our series is geometric, we know that it converges if the common ratio has a magnitude less than 1. If it's telescoping, we form our S sub n and take the limit. Those are the only two series where we're going to find S. Now we have to deal with the rest. So first thing is the divergence test. So the idea is that somebody gives us a series and we have to analyze, does it converge or diverge? It's not geometric, it's not telescoping. What do we do? This is the first thing that we should always think about at least. Maybe we don't write it down, but we at least think about it. So this says, if a series converges, the terms must go to 0. It's necessary that the terms go to 0. So, and we've looked at lots of these things. So the series must have terms that go to 0. So if we look at something like this, the terms are going to 0. So that series is a candidate for a convergent series. And this one will, in fact, converge. So this one does converge, and it converges to, I think, pi squared over 6 or something interesting. I'll just say that it converges, though. This series is the harmonic, and we are going to see that this series diverges. So what we say is that it's necessary that the terms go to 0. You have to be eventually adding insignificant amounts. You must have terms that are getting closer and closer to 0 for there to be a chance at convergence. But just because the terms are going to 0, that's not enough. So it's necessary that the terms go to 0, but it's not sufficient. Just because you're adding terms that are smaller and smaller and smaller doesn't mean that you will end up with convergence. So not only do they have to be going to 0, they have to be going to 0 pretty quickly. So again, that's what we're trying to analyze. What does it mean to be going to 0 quickly? So our first test here basically gets rid of some of the more blatant examples of things that are definitely not going to converge. Like if we have something like this. If we add 1 to itself repeatedly, obviously that's going to go to infinity. That's not going to be a finite result, right? If you add 1 to itself, if you add any number to itself repeatedly, if we add 1/1,000,000th to itself repeatedly forever, that's going to go to infinity. So the divergence test simply says this. If the limit of a sub k is not 0, the series has to diverge. So this is a quick little limit question. We look at the a sub k, like if we look at this a sub k, the limit of this a sub k is 0. If k goes to infinity, we get 0 minus 0, so that's 0. So that tells us that this series might converge. We look at this series down here, we take the limit. What is the limit of the a sub k here? 1, because we have equal powers. So the limit is the ratio of the leading coefficients. Or you could divide everything by k cubed and see that you would have 1, 1, and 1 over k cubed. And so the 1 over k cubed would go to 0, and the overall limit would be 1. However you see it. So if that limit is 1, what can we conclude instantly? It has to diverge. The only way we have a candidate for convergence is if this limit is 0. If this limit's not 0, instantly you know that it diverges. So the divergence test catches egregious divergence. Okay, there's other series that will diverge that, Right here, the limit is 0, but it still diverges. It's going to catch the egregious cases, though. So if the limit is not 0, you know instantly it diverges. The divergence test can never be used to show convergence. It's just showing us that this is a candidate for convergence. The limit of this is 0, so it might converge. It's a candidate. We have to do another test. So the divergence test never gives convergence. It only can give divergence. There's two options. If the limit is 0, then the test is inconclusive. We don't know, does it converge or diverge? If the limit is 0, the result of the test is inconclusive. We have to do more analysis. It still could converge. It still could diverge. So it's one option is inconclusive. The other option is divergence. So if that limit is not 0, instantly we know it diverges. If the limit is 0, then it's inconclusive. We have to do more work. So coming down here, let's take our limit of a sub k. So the limit of a sub k as k goes to infinity. Let's do the division by k cubed, just because that's a pretty easy way to see that the limit is in fact 1. And then our conclusion is divergence. Must diverge. Because that's, and I should put in here, the reason that it diverges is because this is not 0. And I want to make sure that that's clear. So this is not equal to 0, therefore it diverges. Same idea down here. So the limit of a sub k as k goes to infinity here is going to be the limit of k divided by natural log of k as k goes to infinity. Let's see. So the limit of a fraction, we take the limit of the numerator, that's infinity. Limit of the denominator is infinity, so we get infinity over infinity, so we can use L'Hopital's rule. So I usually do this kind of thing over the equal sign just as a marker. It's like, oh, that's infinity over infinity, so we can use L'Hopital's rule. So we take the derivative of the numerator and divide it by the derivative of the denominator. The derivative of the denominator is 1 over k. And what is the limit at k as k goes to infinity? Infinity. This is not equal to 0. Therefore, it has to diverge. If that limit's not 0, then we instantly know it diverges. So in our mind here, there's a couple of things that we want to be doing. When we see fractions, we sort of want to think about pace at which things go to infinity. When we look here, the numerator is a cubic, the denominator is a cubic. They're going to infinity at the same rate. The only way we can get a limit of 0 is if the denominator is going to infinity faster. When we look here, numerator is going to infinity at a whatever pace. But we think about, so y equals x looks like that, y equals k. Y equals natural log of x or natural log of k. Right? That's going to infinity, but much slower. So we sort of think about the pacing here. That one, exponential in the denominator, that goes to infinity faster than any polynomial. So our suspicion right here is that the limit should be 0 and that this might converge. So let's do the math. So here the limit as k goes to infinity of k squared over 2 to the k. Okay, so this again is a L'Hopital scenario. We have an infinity over infinity. So L'Hopital says if you have a quotient where top and bottom both go to infinity, take the derivative of top and bottom and analyze the quotient of derivatives. The derivative is the best linear approximation. So the ratio of best approximation should do the same thing. So let's check. The numerator's derivative is 2k. And who can remember derivative of an exponential is itself times
Natural
natural log of the base. All right, that still goes to infinity. But it's a little bit better. We can see the pattern. We can see what's happening. If we differentiate the numerator one more time, we'll have a constant. And so that's what we're going to do. We'll do one more L'Hopital. One more L'Hopital. Derivative of the numerator will be 2. Derivative of the denominator. Okay, we've got the exponential. Its derivative is itself times the natural log of 2. And then we have a constant that just comes along. So we're going to end up with natural log of 2 quantity squared. Now we're good to go. The numerator is constant. The denominator is growing without bound. So the fractions are going to 0. So our conclusion here is inconclusive. So the divergence test tells us do more work. That's what it's telling us. Do more work. Okay. This one, we have a factorial. So remember, something like 6 factorial is 6 times 5 repeatedly down to 1. So that's the factorial. And when we did growth rates last week, factorial grows faster than any exponential, any polynomial, any log. There's only one function that we're going to see in this class that grows faster than the factorial. That's the power tower, which is k to the k. So here, we do have a L'Hopital situation, infinity over infinity, but we can't take the derivative of k factorial. So the only thing we can do is use growth rates in a case like this. The denominator is going to go faster towards infinity than k cubed. So this limit is going to be 0. Exactly. And all we can say here is by growth rates. So we can't do math here. Up here, you could make the argument with a growth rate argument, but that's not enough. If you can do the math, do the math. We only use this, we only resort to this growth rates argument if we can't take a derivative. So therefore, this one is going to be inconclusive also. So that's the divergence test. And you don't always have to write it down unless that's the problem. If the problem says use the divergence test, blah, blah, blah. Like the worksheet has a bunch of divergence test ones. And you want to do the math. But in practice, we sort of, if someone just gives you a random series, we look at the series and we sort of usually just do it in our head. We say, okay, the limit's 0, we have to keep going. We're going to use the telescoping series method here. So you don't often write it down, but you should always be asking yourself, what is the limit of a sub k? So here is that classic harmonic. So 1 plus a half plus a third, etc. And this diverges even though the terms do go to 0. So this is kind of a really good series to have in your mind because it's an example. It's a counterexample of, well, the terms are going to 0, it must converge. No, this is a counterexample. The terms are going to 0, but it diverges. So let's get a better sense of why it diverges. Whenever we look at a series, we analyze the series by looking at its sequence of partial sums. So S sub n is the sum of the first n reciprocals, sum of the first n terms. And what we're going to do here is look at an integral and make a comparison case. So the function 1 over x, right there. And then we're going to draw some rectangles to represent the sum of this S sub n. All right, so we're thinking about these points right here. Okay, so 1, is the area of that rectangle. 1/2 is the area of that rectangle. Everybody agree and sort of see that each of these is corresponding to the area of a green rectangle? Isn't this inequality true? That S sub n is bigger than the area under the curve from 1 to n plus 1. So if we're going to look from 1 to n plus 1, so right there, all right, that's just the regular definite integral, area under that black curve. S sub n is bigger than it, right? S sub n punches up through the top of the curve and we have extra area above the curve. So we all agree that that's true. So then we come down here and we say, okay, well, what's the integral? What's the area under the curve? So the integral, the function is 1 over x. We know that the integral of 1 over x is natural log of x. Natural log of absolute value of x, but we're dealing with positives, so we don't need the absolute value. So the integral of 1 over x is natural log of x. Plug in the upper limit, plug in the lower limit, and we get this, and this goes to infinity. So if the area under the curve is going to infinity as n is going to infinity, then S sub n, which is bigger than the area under the curve, must also be going to infinity. So therefore, we end up with divergence. So that proves to us that the harmonic series diverges. Harmonic series diverges. Okay. So this is our first real test. So far, we've had geometric series, which is more of a pattern than a test. You know, it's a type of series. We've had the telescoping series. Same thing. It's not really a test. It's a type of series. And then we have the divergence test, which is it's a test, but it's kind of just it just tells us it can only find divergence. It can't find convergence. So here's our first real test that will tell us both. Series converges or it diverges. It's a full-blown test. So what we're going to do is assume that we have this series, this infinite series, and we're going to correlate it to this improper integral. So if this series starts at 1, we're going to start our improper integral at 1. So those are going to match. And the f sub x is just this. It's just the a sub k. It is whatever that function is right there. So these are going to be the same thing. It's just that we use an x instead of a k. So if this is 1 over k, that's 1 over x. If this is k squared, that's x squared. So it's just because we can't do an integral unless the function is continuous. So to create that continuous function, we just turn the n to an x, or the k to an x, whatever the letter is. Okay, so here is the test. The test says that these things do the same thing. They both are going to converge or diverge. We already know how to deal with improper integration. That's what we did in the last test. So we can take our series and we can correlate it to this improper integral as long as you know how to integrate it. Right? So there is the caveat that the integral test will work in all scenarios, but it's only practical if you know how to integrate that function. So if this function is some crazy looking thing that's non-integrable, then it doesn't help us. Then we'd have to use a different test. So the integral test is great when you know how to integrate f. So we'll have a bunch of cases where that's possible. This is a visual to this is a squeeze theorem that shows us that this sort of proves or at least justifies the integral test. And the idea here is that we can look at, you saw this in Calc 1. If you look at these rectangles from a sub 2 on, you can imagine these rectangles being created by looking at this right endpoint right there. So the height of this a sub 2 is the right endpoint, you know, when you do those right and left endpoint approximations. So if we look at the red triangles here, and we just shift them to the left, we have this picture. Okay? So if we take a sub 2 and we just look at it on this side, so over here, if we add up these pink rectangles here, we have this scenario. So these pink rectangles get added together. So we're going to let k go from 2 to n. And those are going to be an underestimate of the integral of the function. So the function starts right here at 1. We're looking at this curve going all the way down to n. So there's 1. That's the left end point there. So it's going to go over to here. And it's going to be the left end point right there. So we get all that. So if we add up all those, and n is right there, and n is the right endpoint of these subintervals. So if we add all those, do you agree that that inequality is true? All right, we look at the sum of all these pinks. Here's n equals 1. Here's n. If we add all those up, that's less than the integral. It's less than what's under the orange curve. All right, and certainly the function's area from 1 to n is bigger than that because we have these extra little triangle things there. And now if we look at this picture where we start at 1 instead of 2, the green rectangles, again, going from 1 over to n. So again, 1 to n in there. So same exact domain. The greens are an overestimate for the area beneath that curve. So we know that the area under the curve is sandwiched in between those two things. That makes sense? And so if this integral converges right here, that means this infinite sum must also converge. The only difference between this infinite sum and this infinite sum is that that's just got one extra term. And we know that if you chop off one term, it doesn't change convergence. So if this integral converges and this is less than it, then it converges. If this integral diverges, this integral is, or this summation here is bigger than it, then this must diverge. And if that one diverges, this one diverges because they only differ by one term. So you can squeeze out the results. So let's take a look at this one. All right, so here we have a function that's easily integrable. We know how to integrate a power in the denominator. Move it in the numerator, use the power rule, use the reverse chain rule. So integral test will make sense here. So we're going to consider the integral from 1 to infinity. So it starts at 1 there, starts at 1 here. The only difference here is that we make this an x instead of a k. And it's easier to integrate if you put it in the numerator. So we have that. Anytime we have an improper integral, the first word that we write down after the equal sign is always, begins with an L, limit. So limit, and did this book use a B or an A? Did it use an A going to infinity?
B.
B, because A was on the left side and B was on the right. Yeah, so B is if it's, yeah, this side. So we have the definite integral from 1 to b, 2x plus 4 to the negative 2 with the dx. This is an easy integral. We add 1 to the exponent, divide by the new exponent. So we get 2x to the, we get 2x plus 4 to the negative 1, divide by negative 1. But we also have to use RCR, reverse chain rule. We look in here, and what is the derivative of 2x plus 4? 2. So we're also going to divide by 2. So we do the power rule, add 1, divide, and then we also divide by the derivative of the inside. This is going to be evaluated on the interval 1 to b. So we have the limit of this negative 2. If we want, we can factor it to the front, so that would be a negative 1/2 since that 2 is in the denominator. It is always easier to evaluate limits without negative exponents, so let's just rewrite that. And this limit is as Well, we're going to have to replace the 1 and the b. This limit is as b goes to infinity. So we've got the -1/2 out in front. We still have limit as b goes to infinity. And let's see, we're going to have 1 divided by 2b plus 4 minus, plugging in a 1, I see 1/6. Where does this part go?
0.
That's going to go to 0. Because the denominator is growing without bound, fractions have to go to 0. So what is our total then here?
-1/6.
So the limit is -1/6, and then if we multiply it by that -1/2, we get a 12. So this is not the sum of the series. This is the area beneath this curve on this interval. This is the area here. And that area might be equal to the series, but not necessarily. So our conclusion is here, so this tells us that the improper integral converges. And then the theorem that we just saw tells us that the series also converges. So this is a positive real number. And what I usually will do is write this just to indicate that it's a positive real. So the little epsilon, when we're talking about sets, means that this number is in this set. This set over here, the real numbers, you use a big R with the double bars. That's the real numbers. And if you put a plus up there, it means positive reals. Positive reals. And so this just says it's a positive real. That means that we have convergence. So therefore, both converge. So both converge, i.e. the series and the improper integral. Both are converging. They both converge or they both diverge. So if you get a number, a positive real number, that tells you that you have convergence. If we got infinity, that's not a positive real number. We would say therefore it diverges. So that is how the integral test is going to work. All right, let's go ahead and take a break. Can we just do 5 minutes since we had all the chaos at the beginning? No more chaos, hopefully, today. Hopefully. Pause. Try not to lose all that time from the beginning. Miniature disaster. All right. Here is another one that we can use the integral test for. Hopefully you see that you can integrate that pretty easily with u substitution. Now on the test, I'm going to be super clear and say use the integral test so you don't have to think to yourself, do I know how to integrate this or not? If I say use the integral test, that means you can integrate it. But when you're just doing random problems, you want to be thinking to yourself, can I integrate that? And so we are going to do the same thing we did up here and look at the improper integral from 2 to infinity in this case. And we just switch everything over to x's. So there is our improper integral. The first thing we always do is write down limit next. So this is the limit as b goes to infinity. And we can put the dx in the numerator if we want, just to shorten it up a little bit. So we have that. And what are we going to use for our u substitution?
Natural log.
And so that's our candidate, right? We always look inside the angle, the parentheses, the exponent. And this only works if its derivative is present. And do we see the derivative of natural log of x somewhere in there? Yeah, we know the derivative of natural log of x is 1 over x. And we see a 1 over x in there. So we're we're thinking that's a great candidate for the substitution. So we're going to have limit. Now we've converted over to u, so I'm going to put placeholder limits here. And we see that the dx over x, that is du. So dx over x is du, dx over x is du. And this is going to be u to the 2 in the denominator, so it's u to the minus 2 in the numerator. And then we can use our power rule. So we're going to get u to the negative 1 over negative 1. So that's negative 1 over u. And these have placeholder limits. We don't know what the u's are. With improper integration, it's usually just best to go back to whatever letter you started with. So we said that u was natural log of x, so we have that. And now we can go back to our x limits, 2 and b. Yeah?
So what's the purpose of the stakeholders?
Well, you could convert everything to u limits if you want, but usually with improper integration, we're taking this limit as b goes to infinity. Then you'd have to convert your limit also.
Okay.
So it's usually easier if you've got this limit as b goes to infinity. It's usually easier to want to stick with the b. So we'll go to u, do the integration, then we'll go back to where we can use the b again.
Okay.
So it's possible to convert everything over, but it's not just converting these limits of integration over, it's converting more than just that. So it's generally easier to go back to the originals.
Okay.
So if we go back to the originals, we're now going to have limit as b goes to infinity of negative 1 over natural log of b minus a minus is plus 1 over natural log of 2. And this first fraction, where is it going?
0.
Yeah, that's going to go to 0. Constant, numerator's constant, bottom's going to infinity, fractions go to 0. So our overall limit is 1 over natural log of 2. And then, so what we have to, in order to conclude that this improper integral converges, it converges as long as this is a positive real number. So I'm going to write this element of the positive reals. That just tells me that it's a positive real. That tells us that the integral converges. And our conclusion is, therefore, both converge. So both the improper integral and the original infinite series, they both converge. Again, it doesn't tell us what this series converges to, just tells us it converges. Okay. All right, you all try this one. So try this one with the integral test, number 26. Yeah. You did. Good. Right? Yeah, when you see that pattern, it's reassuring. Does everyone see the pattern? What form is it going to have?
Log?
Log form? Yeah, log form. Once you get good at identifying that log form, and it kind of jumps right out at you. Oh, it's 5 years. Yeah. Oh,
Can I just double check that I'm remembering how to do the law?
what's that?
Can I just double check that with Trey?
Yeah, exactly.
Okay.
Yep.
So just wanna make sure it's
That
not-
is looking good. So there's our first step. First step is to write down the improper integral. And the way we evaluate an improper integral is to turn it into the limit of a definite integral. And then one of the things we notice right away is that the derivative of the denominator, it's almost the numerator. That derivative is 3x squared, so if we put a 3 in right there and then balance it out by putting in a 1/3 out in front, now we've got log form. And so now we can immediately write down the antiderivative. And if we want, we can factor that 1/3 all the way to the front. Doesn't really matter. Personal preference. So this is going to be limit of, this is now integrable. That's going to be natural log absolute value of the denominator. And then we have our limits 1 to b.
And then upload your stuff to the assignment folder and I'll still try to make it.
So we're going to plug in the b and the 1. So we'll have natural log of b cubed plus 5 minus natural log of 6. And that's as b goes to infinity. And I want to make that 6 look more like a 6 and less like a b. And where's that limit going to?
Infinity.
Infinity. So this limit is infinity, therefore we have divergence. So let's just go back to the original summation and think about trying to generate some intuition. When we look back here, the addition of 5 in the denominator is kind of insignificant. So in your mind, if you cancel out that 5, and then you have this, it simplifies to 1 over k. And the series 1 over k is the harmonic, which diverges. So this is what we would expect. So if we can always get some intuition by kind of getting rid of I'm touching the eraser. Thank you. You can always get some intuition for what the answer should be by doing that kind of thing where you eliminate the pieces of the summation that look insignificant. You can get a sense for what the nature of it is. So the nature of this summation is that it's like the harmonic, which diverges. So that's what we would expect. Okay, now we have one of these totally funky ones, bunch of natural logs in here. And so when we were doing improper integration, we saw that the integral of 1 over x diverged. We also saw that the integral, so we saw this, the integral of 1 over x obviously diverges. We saw that 1 over natural log of x times x, let's put the x times on the outside, so x ln x in the denominator, we saw that that diverged also. Now they're adding another wrinkle here. And if you remember, you may not, but we also did the integral of dx over x times natural x quantity squared. That one converged. This one's kind of in the middle. So we saw that if you had an x, natural log of x, it converged. Now they're slowing it down a tiny bit. Oh my gosh, why there? They're slowing it down a tiny bit. This quantity right here is going to go to infinity, but it's going to go to infinity slightly slower than natural log of k. All right, so natural log of k goes to infinity. Natural log of k goes to infinity a little bit slower. So we showed back in the improper integral section that if we had x, ln x, we had convergence. Now they're saying, oh, well, let's just slow this one down a little bit and see if we still have convergence or not. So that's what they're doing. So let's check. So obviously the first step is to write down the improper integral. So we're going to go from 3 to infinity in this case. And then we have dx over x, ln x, and then ln of x. This becomes limit as b goes to infinity, 3 to b. And then we have the same exact integrand. X times ln x times ln x. Okay, so u sub is pretty obviously what we want to try. And what do you think we want to let u equal?
Natural over that.
Not enough. Natural log of x. We're going to let u be this one. Because if we let u be natural log of x, the derivative is 1 over x, which is present. But then what do we do with that thing? Then we're going to have natural log of u. So then in the denominator, we're still going to have a product. And we'd have to do, we could get away with doing it with multiple integrations. But watch what happens here. If we let u equal natural log of x, so this natural log is inside. So the derivative here, du, is 1 over what's inside multiplied by the derivative of what's inside. Well, the derivative of what's inside is 1 over the inside of it. So we end up with 1 over x ln x. So this is 1 over x ln x dx. So this whole chunk right there can all be replaced then with du. So that's going to simplify it tremendously. So we're still dealing with the limit. We're going to put in some placeholder limits because we want to come back to the b. So now we're going to have, let's see, isn't it just 1 over u du? All right, so the dx and the x and the ln x, that all becomes du, and this just becomes 1 over u. So we have 1 over u du. Oh, we know how to integrate that. That's going to be natural log of absolute value of u with our placeholder limits. Now we're going to go back to x's. So limit of natural log of natural log of natural log of x. And we don't need the absolute values. We're back in x's, and the x's are greater than or equal to 3. So we have positive on the inside. All right, and our limits go back to the x limits, so 3 to b. 3 to b. So we're going to have limit as b goes to infinity of ln of ln of ln of b minus ln of ln of ln of 3. And that limit as b goes to infinity, infinity. So therefore we have divergence. Okay. So that thing right there goes to infinity. It goes to infinity very slowly, but it still goes to infinity. It's not going to a constant. So divergence. Any questions on any of those steps?
Couldn't we have deduced that since we know that 1 over x diverges and 1 over x ln of x also diverges?
So 1 over x diverges. This denominator is going to go, so when we have x ln x, this denominator is going to go to infinity faster than that goes to infinity. So this one has a chance to converge. Does that make sense? Do you agree that x ln x goes to infinity faster than x?
Yes.
Right? And so then if we put in another ln of whatever here, this denominator is going to go even faster to infinity. So there's still a chance it could converge. Because this is going to go a little bit faster.
Oh, okay, I see.
So when you're because this thing is bigger than 1 eventually, right? The quantity here that I've got highlighted is bigger than 1. And when you multiply a given quantity by something that's bigger than 1, it's bigger. And so maybe right in the beginning, this looks like it's shrinking the denominator, but it's not. This is increasing the denominator in the tail. As soon as we get a little bit further, as soon as this thing is bigger than 1, it's creating the denominator, it's making the denominator go to infinity faster than it was. Does that make sense? So there's a chance that it could converge. Now, if you were multiplying this by, say, 0.9, well then, yeah, if you know what's happening to 1 over x ln x and you multiply the bottom by 0.9, it's going to shrink the denominator, and so that for sure is still going to diverge. But if you're growing the denominator so that the fractions are going to 0 faster, then it could converge.
Okay.
So it's maybe counterintuitive when you look at this that this is actually making the denominator go to infinity faster. But if you think in your mind, if you multiply a given quantity by something bigger than 1, that grows it. Right? And this is bigger than 1 eventually. Maybe the first couple of k values it's not, but they started at 3 anyway, so I bet they started at 3 for that reason. But it wouldn't matter. As long as it's eventually bigger than 1, it's going to cause the denominator to go to infinity a little bit faster. Yeah. Not totally intuitive. All right, so now let's look at a cool type of series called a p-series. So this is number 5 in the list of tests. Geometric, telescoping, then we have the divergence test, and then we have the integral test. I believe we have 10 total. So we're coming up to the halfway point. P-series. So P-series should be super intuitive because it should remind you of what we did in the last chapter when we had improper integration where the denominator was just the power of x. Instead, we have this infinite series, and the exponent's not an x, it's a p. But what we saw back in that chapter was that integral of 1 over x diverged, but integral of 1 over x to the 1.1 converged. As long as the power on x is a skosh higher than 1, you have convergence. So 1 over x diverged, but 1 over x to the 1.1 converged. So that's the p-series. So the p-series says if the power, p for power, if the power is bigger than 1, you will have convergence. So the p-series is more of an acknowledgement. It's like, oh, this has the form of a p-series. Let's identify p. And then if p happens to be bigger than 1, we can conclude divergence. And if it's less than or equal to 1, we have bigger than 1, we have convergence. Less than or equal to 1, we have divergence. Okay, so let's first see if we can put it in the form of a p-series. So that's the form we're targeting. So we have our summation. K is going from 2 to infinity. And we want this to be in the form of a p-series. Well, the first thing I notice is that K is the base for both of these. So this is e to the, or K to the e minus pi if we put it in the numerator. All right, upper exponent minus lower exponent. Still not in the form of a p-series. P-series is 1 over k to the p. So we want to push this exponent into the denominator. So this is going to be k to the
Negative e plus pi?
It is already, oh, what did you say, negative e plus pi? Yes, exactly. So we multiply that by negative 1. Yeah, what you said. That's right. Negative e plus pi. And k will still be 2 to infinity. Yes. Perfect. So that is the new exponent. Now it's in the form of a p-series. P-series is 1 over k to the p all the time. So now we can identify p. So here's what I need to see on the exam. You need to identify p. This is how I know you know it's a p-series. You identify p, and now you compare it to 1. So we have to decide, is this bigger than 1 or less than 1?
Bigger.
It is.
Yeah.
3.1 minus 2.7 is bigger than 1? So if you need your calculator, so we have e is at 2.7-ish and pi is at 3.1-ish, so it's about 0.4-ish.
Oh.
Right.
Bigger than 1.
So this is less than 1. Less than 1. So now I know that you identified p, you've compared it to 1, you've said it's less than 1, and then you make your conclusion. So therefore diverge. So there's not a ton of work with the p-series. It's more, you have to convey that you know what p is, you have to convey that you know you're comparing it to 1, and then you have to make your conclusion. So you see it now?
It's like, oh, pi is bigger than e. It's
Yeah.
gotta be
Pi is bigger than e. I agree.
So it's a positive number.
Pi is definitely bigger than e. So there's a
Positive e.
possibility. Okay, so let's try this one. So lots of these ones were trying to trick us and try to make it not so obvious. Well, why do I have so much space in these? So let's take a look at 32. So what do we think? Okay. So earlier we talked about constants can factor out of a summation just like they factor out of limits and derivatives and integrals. So we see this 2 here is not part of that exponent, right? That 2 can be factored to the front. Here is how I would rewrite this. I would say, okay, well, let's factor the 2 out. And we know from that theorem we just saw a minute ago, if you have a series that converges and you multiply by 2, still converges. Multiplying by a non-zero constant is not going to change anything. So we can do this. And now a p-series, we want to have the k in the denominator. So this is what we would end up with if we wrote it in the form of a p-series. So 2 times a p-series. And what is p here?
3 halves.
So p, we have to identify p. So now I know you know it's a p-series. If you write down the letter p and say p equals 3 halves, I know you have now acknowledged it's a p-series. And then we have to compare that to 1. Is that greater than 1? And then we have our conclusion, therefore, converges if it's greater than 1. So that's all you need to do for a p-series. Put it in the p-series form, identify p, compare it to 1, make the conclusion. So p-series, for a lot of people, feels like the easiest of all the tests. Plus, it's very similar. If you think about the integral, the improper integral, if we had integral of 1 over x to the 3/2, it's back to what we did in the last chapter. As long as the exponent was bigger than 1, you had convergence. So it's kind of the most familiar. It seems like the test with the least work based on what we've already done. Oh, yes. Okay. So this guy, same thing. We want to try to rewrite this. So let's first do this. So we want to try to put it in the form of a p-series. So we're going to look at that denominator. The first thing we're going to do is write it as a fractional exponent. So 27 times k to the 2 all to the 3rd power. So it's still not 1 over k to the p. So let's keep going. So it's not where we want it to be quite yet. So we can do the 3rd root of 27. 3rd root of 27 is 3. K to the 2/3. And then to be super specific, we want it to be 1 over k to the p. You could sort of stop there, but this, we've now identified the series part of this as a p-series. Now, the constant can factor out to the front. Now we have a constant times a p-series. Let's identify p. P will equal
2/3.
Yeah, 2/3. It's the power on k as long as k is in the denominator. Compare this to 1.
Less than 1.
So therefore diverge. So p-series, bigger than 1, converge, less than 1, diverge. Is that all good? P-series, we like you. All right. All right, so choose your test. The divergence test is that test that we did at the beginning of class. If the limit of a sub k is not 0, it diverges. Again, that's something we should at least consider every single time we look at a series. If we go back to the previous slide for a second. So when you look at this, so in your mind, you take the limit of this, you should see that the limit of this is 0, so it might converge, right? Limit of this, if we go right here, oh yeah, limit is 0 because the denominator is going to infinity, so it might converge. Here, maybe it's not as obvious, but still, you know that this power on the k is what would you say here? What would you say the limit of this k e to the pi is as k goes to infinity? What do you think that power is? Or what do you think that limit is? Does everyone agree?
Yeah.
So let's just look at an estimate here for a second. So if we estimated so our goal is to take the limit of a sub k. So if we wanted to take the limit of this, let's just estimate this exponent. So we have 1 over k to the, so we said 3.1 and 2.7, so what do we say, k to the 0.4? So as k goes to infinity, where does that go?
Approaches 0.
So has everyone seen? So if we have k to the 0.4, as k goes to infinity, what is happening with the denominator? Is it a bird wing? Right? The denominator is a bird wing. Right? So like the square root of k, bird wing. K to any fractional exponent is bird wing, right? In quadrant 1. So the denominator is going to infinity. Everyone agree? Like if you imagine the square root of k, square root of k looks like that. Any of those truly fractional exponents on k create that birdwing. X to the half, x to the 1/4, x to the 3/4, x to the 9/10. They all look the same. So the denominator is going to infinity, so this limit is 0, so that divergence test would be inconclusive here. So the divergence test so that's why we have to do more work. Right? So anytime we're looking at these, now the p-series is so specific that you don't really even have to consider the divergence test, but it's a good thing in your mind to always think about. Is the limit of a sub k 0? Because if the limit of a sub k is not 0, then instantly you know it diverges. Okay, so when we look at this next one right here, what is the limit of a sub k here? 1. So limit of a sub k, as k goes to infinity, is the limit of this square root. And if we want to get really nitty-gritty, the square root is a continuous function, so the limit can go inside the square root. We usually don't write that step, but that, hopefully in your mind, you're seeing that when you evaluate this limit here, you're pushing the limit inside. And if you take the limit of the inside and get a number, then you just take the square root of that number. And now we're to the place where you can do it one of 3 ways. You can do the polynomial, the college algebra method. Oh, the polynomials have equal powers. Limit at infinity is the quotient of leading coefficients, 1 divided by 1. Or you can divide everything by k, so that you would have, which is the way that usually in my mind, that's usually how I see it. You're doing this kind of thing, dividing by the k, and the 1 over k goes to 0. So the limit of that thing is going to be 1. Or the third option is L'Hopital's rule. You could take derivative top, derivative bottom, you get 1 over 1. So 3 ways that you can evaluate whatever your preference is. So the limit of a sub k is 1, and this is not equal to 0, therefore diverge. So the divergence test says if the a sub k's don't even go to 0, there has to be divergence. Right, the limit of a sub k must be 0 to even contemplate that there's convergence. So if the limit of a sub k is not 0, that's an egregious case. There's no way it converges. Okay. This one. Is there a test here that comes to mind? So the integral test is going to work here because we can integrate that, right? This is sort of an inverse trig, inverse tangent one. Is that a p-series?
Not yet.
Not yet. It's not a p-series yet. We have to, because the p-series, certainly if there was no 9, 10 over k squared, we could factor out the 10, and then we'd have 10 times the p-series. This, as it's written, is not a p-series because we have the plus 9. We are going to learn on Thursday a couple more tests, one of which is called the comparison test, and that's what we can use instead of going to the integral test here. If we have a p-series-ish series, we can use a comparison test, which we'll get to on Thursday. At this stage, what we're going to want to do is use the integral test. So we are going to, if we factor out the 10, so the 10 is just a constant. It can factor to the front of the summation. And we end up with this series. So it suffices to look at the integral of just that thing. We can ignore the 10 because we know a 10 doesn't do anything. Multiplying by a constant doesn't change anything. So what we're going to consider is the integral from 0 to infinity of dx divided by x squared plus 9. So if that improper integral converges, then the series converges. If that improper integral diverges, the series diverges. So first step, we're going to pull the important limit to the front. We're going to put a limit in the front. We're going to make it 1 or 0 to b. So we have this scenario. So now we have a definite integral, limit of a definite integral. The way we've been doing this is to factor out the 9. I'm going to factor that all the way to the front. So that 9 is in the denominator, so it comes all the way to the front. Integral 0 to b, that is a 0, not a 6. And here, when we factor out that 9, there is no 9 here, so we're doing that kind of thing. And we're factoring that 9 out to get that. So we have x squared over 9, which is x divided by 3 squared. Plus 1. Now we have an integral that's in the form of an arctan. That is in the form of an arctan. So we will have 1/9 limit. This is going to be arctangent of whatever's in the parentheses, so arctan of x thirds. In the parentheses is not just an x, it's a function of x, so we have to use the RCR, reverse chain rule. And what is the derivative of what's in here?
1/3.
1/3 is the derivative. Right? And we have to divide by 1/3, which means multiply by 3. So we take the reciprocal and multiply it, 3 over 1 if you want to put the 1 in. And then our limits of integration are 0 and b. So we end up with 1/9 multiplied by limit. Oh, actually, we can pull out that 3 as well, right? Oops. So we can pull out the 3. So 3 over 9 is 1/3. And then limit. We're going to have arctan of b thirds. Arctan of b over 3 minus arctan of 0. And what is arctangent of 0? So we can do it 2 ways. You can visualize the graph of arctangent, which has that shape to it. So arctan of 0 is 0. Or you can go to the definition of arctan. This says, what is the value? What is the angle on the right of the unit circle where the tangent is equal to 0? Tangent is 0 right at 1, 0, that right-hand point of the unit circle. So 0 radians. So this, that's equal to 0. And where does this one go as b goes to infinity? Pi halves. That is going to go to pi over 2. So that horizontal asymptote. So our overall value then is pi over 2 times 1/3, so we get pi over 6. This is a positive real number. Therefore, both converge. So as long as you get a positive real, that tells you the improper integral converges, and if the improper integral converges, that tells you the series converges.
Why is it pi over 2 for the tangent, the inverse tangent be over 2?
So this is a graph of inverse tangent. And it's got a horizontal asymptote at pi over 2. So as x goes to infinity, inverse tangent gets closer and closer to pi over 2. And if you were going the other direction, there's also a horizontal asymptote at negative pi over 2, if you took the limit as x goes to negative infinity. Arctan is going to show up the most often because of this, because it has a limit. as x goes to infinity. All right, let's take a look at that thing. Any ideas? Does it remind you of something we've already done?
U-sub?
U-sub's not going to work here because these things are different. PFD, partial fraction decomposition. So if we do PFD, we can turn it into like an A minus B and use telescoping. So we have to use PFD here. So PFD, we've got this factored denominator. And this factored denominator, we're going to write it as a pair of partial fractions like that. So our goal is to use the integral test, but the integral is only going to work once we do the PFD, so let's do the PFD first. So we end up with 1 equals a times 3k plus 4. And b multiplied by 3k plus 1 both of these denominators are linear, so we can use the convenient value method. What is the convenient value for this denominator right here? What makes that 0?
1/3.
Negative 1/3?
Sorry, negative 1/3. Yeah.
Negative 1/3. So we're going to plug in k equals negative 1/3 across the board. So plugging in k equals negative 1/3 here and here. Here it gives you a 0. Plugging in negative 1/3 there gives us negative 1 plus 4, which is 3. So 3a equals 1. So a is 1/3. The second convenient value is from when this is 0, which is going to be negative 4/3. So now we're plugging it in across the board here. Negative 4/3 there gives 0. Negative 4/3 here. Negative 4/3 times 3 is negative 4, plus 1 is negative 3, so we get negative 3b. So b will be negative 1/3. All right, so we have, now we've broken it apart. We've turned that product into two partial fractions. So we're going to consider the integral from 1 to infinity of, let's see, a is positive 1/3, so let's write it this way first, and then we'll factor it out. So we have that, and then minus 1/3 over 3k plus 4. Oh, and I want to make this x's. Because we are now dealing with an integral, so as soon as we have an integral, we want x. So we have that. So let's go ahead and factor the 1/3 out to the front and convert it to a limit as b goes to infinity. So we have this. What am I doing? What am I doing?
Good question.
Yeah, great question. All of a sudden I'm going to the integral test. Is the integral test the test we want to use? No. Because the integral test, what it's going to show, if you were to integrate this, aren't you going to get a log and a log? And the integral, if you get a log minus a log and both the logs are going to infinity, you get the indeterminate form infinity minus infinity. So integral test is not going to get us anywhere. Is everybody seeing this? Like if we integrate 1 over 3x plus 1, that's log form. If we integrate 1 over 3x plus 4, that's log form. So you'll end up getting two logs, both of which are going to infinity. Infinity minus infinity is indeterminate. So integral test is not the way to go. Integral test, Integral test is not the way to go. We want to use I mentioned it, but then I didn't do it. We want to use the telescoping series technique. So this is going to be the series. A is 1/3. So we're going to have 1/3 over 3k plus 1 minus 1/3 over 3k plus 4. And this series is 1 to infinity. That's what we want to use. So let's factor out the 1/3 though. It's going to be easier to deal with this with the sequence of partial sums without that 1/3 in there. So we're going to have 1 over 3k plus 1 minus 1 over 3k plus 4. Okay, so we're going to think of S sub n. S sub n is the sum of the first n terms. Let's come down here so we have plenty of space. So S sub n, plug in the 1. So we're forgetting the 1/3 for now. Let's forget the 1/3 because that doesn't change convergence or divergence. So ignore the 1/3. So S sub n, we're going to plug in a 1 first. So we're going to get 1 plugged in for the k. So I'm seeing a 4th minus, am I seeing a 4th minus a 7th? Is that what you see?
Yeah.
1/4 minus 1/7 plus, now let's plug in a 2, and I see a 7th minus a 10th. And then let's plug in a 3, and we get a 10th minus a 13th. Let's just go 3 terms should be enough, I believe. So the k values that we're using are 1, 2, 3. We want to go to n, so we're going to have an n minus 1 and an n for our k values. So plugging in n minus 1 next. So plug in n minus 1 right here. Got to do some arithmetic. So plugging in n minus 1, that's going to be 3n minus 3. So we're going to end up with 3n minus 2 minus n minus 1 here, 3n minus 3, so we're going to end up with 3n plus 1. Plus, and then we plug in the n, that one's pretty straightforward. So we have 3n plus 1 minus 3n plus 4. All right, so there is our S sub n. The cancellation stuff, start on the left, go left to right, second with subsequent first, second with subsequent first, second with subsequent first somewhere in the muck. And then we convert and we want to go right to left. If we look here, we can establish the pattern pretty easily. First with second of prior, first with second of prior. So first with second of prior, first with second of prior. So that tells us that S sub n is equal to 1/4. Everything else is canceling, minus 1 over 3n plus 4. So that is S sub n. The limit of S sub n as n goes to infinity is equal to 1/4. So therefore, S equals 1/4. In other words, we were trying to figure out if it converged or diverged. So if S equals a positive real number, that tells us that the series is converging to that positive real number. So this series, we can give more information. So the question just said, does it converge or diverge? But with this series, we actually can be more specific. It converges to 1/4. So that series telescoping and geometric, we can find what the series converges to.
You don't have to plug in the 1/3 at the front of the summation.
The good point. So it's true that the series converges. Saying S equals 1/4 is just for this part of it. So if the question said, what does this series converge to? Yes, it is
We multiply it by 1/3.
1/3.
To get 1/12.
Yes, yes.
Okay.
Yeah, thank you for saying that. So this 1/4 is only for this part of it. So if we want if the question said, what is the sum of the original series, it would be 1/12. Yes. Yeah. Make sense? Question?
So you said it's because 1/4 is a positive.
Positive real. Yeah. So if it's a positive real, then we have convergence. Positive real. When we get to alternating series, we could have a sum that's 0. But right now we're dealing with a series of all positive numbers. We'll see when we get to alternating, you can have some other things happen. When do we get there? All right, so, okay. So this slide looks intimidating. It is intimidating. And this is a topic that will come up later in engineering courses where you end up with an infinite series and you can use an integral to approximate it. So we've talked a little bit about the fact that if it's telescoping or geometric, we can find the sum. Most series, we can't find the sum. But what would be helpful is to get an approximation. And in this class, we're going to talk about it just for a few minutes. But when you get into an engineering class or an applied math class, like a numerical approximation class, you'll use integrals to approximate your series. So, what we are saying is the following. So we've got this convergent series, and we are going to think about truncating the series and creating a partial sum. So going from 1 to n. So S sub n is the sum of the first n terms. And the remainder is going to be tied to your S sub n. So if your series converges to a number, but you truncate it so you only look at, say, the first 1,000 terms, then there's going to be a little bit of remainder. Right? If you look at that first 1,000 terms, you may be super close to the actual sum, but you're not going to be all the way there. So we're going to think of the sum of the series, we're going to think of that S sub n plus a remainder that's associated with that n value. So your S sub 1,000 is going to be the sum of the first 1,000 terms, and then your remainder will be called R sub 1,000, which will be the sum of the tail. If you have S sub 1,000,000, that's going to be even closer to the true sum. And your R sub 1,000,000 will be that little tiny difference. So you've got a series that converges to S. Your partial sum is going to get closer and closer depending on how big your n is. And then your R is going to get littler and littler. But the subscript of the R is always going to match the subscript of the S. So think of R sub n just as a number. It is whatever the total sum of the series is minus your partial sum. So think of it just as a number. Okay, so the remainder, let's take a look at this picture. And the idea is that a lot of times when you're in industry or doing engineering type problems, a goal is often to minimize the remainder. Like you're filling cans of Coke and you want to be within 0.1 ounces of 12 ounces. You want to minimize the variation. And so the idea is to come up with a threshold for that remainder so that you're not spending too much money to be more precise than you need to be. And so let's try to understand this, that the remainder is less than the integral from n to infinity. So if we look down at this picture, the blue rectangles are representing a visual for S sub n. So if we add up the first n rectangles here, that's going to be S sub n. The remainder is going to be what comes next. So the remainder, so if the blues are S sub n, then R sub n is going to be the beiges. It's just the rest is the tail. Okay. So this is one visual. Everyone agree on that visual? That we can visualize it this way? If we form these rectangles to the left of each of the index values, right, to the left of 1, to the left of 2, to the left of 3, to the left of n, those are the blues. Now we can do that shifting type of thing, and we can imagine our rectangles being to the right of our index values. So if we move our rectangles to the right of the index values, then this is a visual. We have the same blue rectangles, same exact blue rectangles, except this blue one, when it gets pushed to there, the right endpoint is now n plus 1. Everyone agree with that? That that's just another visual of the same exact data, the same blue rectangles and beige rectangles, same ones. So the remainder is always the beige. We can see that the remainder is under the red curve from n to infinity. Right? So the remainder is the beige. It's under that integral. And if we look down below here, we can see that the remainder, it's the beige, is bigger than the integral from n plus 1 to infinity. So the remainder is always trapped in between those two integrals. So that's what this visual is giving us. It's giving us that the remainder is always between those two integrals. And those two integrals are, so here's our series. We've got our partial sum right there. We found our S sub n. And then we have our two estimates for the remainder. So the remainder is trapped in between those two. So if we use that integral there, that's going to be an upper estimate for the summation. And if we use this integral here and add that to S sub n, that's going to be a lower estimate. So the remainder, the important thing about the remainder is that it's just trapped in between those two integrals, those two improper integrals. Now in this class, we're not going to get into the weeds on that. It's more of a concept at this point. It's more of a concept that you can figure out bounds on your remainder so that if your goal, the hard thing is to then translate that to how many terms do you have to add up so that your remainder is smaller than that specific number. What we are going to do in this class in analyzing remainders is to analyze one type of remainder, and that's going to be for a particular type of series called an alternating series, because analyzing the remainder in an alternating series is as simple as it gets when it comes to analyzing remainders. Just looking at this equation and that integral, you can understand that analyzing remainders can be a pain in the butt because you're dealing with these improper integrals. Right? These are both improper integrals, so it can be a real hassle, a lot of work. But with alternating series, it turns into a really simple evaluation. So we're going to focus on the alternating series, give you a sense of how to analyze a remainder, and when you get into a more numerical analysis type class, you'll do it with integrals. And it'll be harder. It will be harder. So let's talk about this just for a moment. This is an optional topic, the Riemann zeta function. And the Riemann zeta function is something that is used in math to predict density of prime numbers, which is completely weird. So first off, the Riemann zeta function has this form, 1 over k to the x, and if you pick specific x's like these evens, 2, 4, and 6, you can actually find what these sums equal to. This particular one, 1 over k squared, is called the Basel problem, and you should watch that video. It's a really cool rendition of how Euler came up with pi squared over 6 as this particular sum. Super interesting how he did it. Now, second interesting thing here, this is an infinite sum. Why in the world would an infinite sum have anything to do with prime numbers? That's the first question. It's like, well, When I look at these things, you see no prime number. There's nothing to do with prime. Pi is in there. That has nothing to do with a prime number. So here is a crazy theorem. And if you look it up on the Google, you'll see it. This equates an infinite sum with an infinite product where all of those p-values are prime. So this turns a sum into a product with only prime numbers. And if you look it up, the proof of it's only a page. It's remarkably simple for something that looks absolutely crazy complex. So you can prove that this infinite sum is the same as this infinite product, and that's why there is a connection to the prime numbers, because of this. So super interesting. You can look at that video about how you get the sum of the reciprocal squares, and if you just Google, you can see how you can prove the infinite product. The Euler product is equal to this infinite sum. So super interesting. In your free time. In your free time. All right, well, let's stop there and see you all on Thursday. We are grateful that we had no crashes. The teacher in here yesterday had crashes. What was that?
After the first one.
Yeah, very good.
That one wasn't really a crash, actually, after all, though.
Yeah, no, it just didn't work to begin with.
The cable that looked plugged in was not plugged in.
Ah.
You gotta try that first.
I know.
Like, push them on.
I should know that by now.
Try turning.
Just shove all the cables. Okay.
I've heard that that's like half of people in tech support, like what they tell me. Did you try turning it off and turning it on? Oh, it's working now? Great.
Oh, okay, thank you. Try that before you call me.